Hi, good evening, and welcome to my daily live session on topics for execution excellence. My name is Dinakar. I am the founder of Samuthana and the inventor of Do How, a methodology for driving teams to achieve challenging goals and amazing outcomes. And while doing so, to get them to acquire leadership skills by changing their mindset and acquire management skills by progressing on the smart manufacturing journey. So that's the core value proposition that we bring to the table. And we primarily work with manufacturing companies. Of course, we have clients from other sectors too, but primary focus is on the manufacturing sector. And that's a very brief introduction of what I do. And with that very brief introduction, let me directly jump into the topic of the day, which is something to do with smart manufacturing. I'll talk about that, the product cycle. Before doing that, I would like to invite you to visit our website, dinakarmurthy.com it is, or write an email to me in case you want to talk to me or let me know something and or provide me with a comment or a feedback. That I would be more than happy to receive your comments and feedbacks. With that, thanks a lot. Now let me directly jump into the topic of the day, which is about smart manufacturing. And before I start, let me give you a very quick recap. Smartness is basically about trying to control and make sure that the control is continuously improved, and there is a learning happening there, and that happens basically with the PDCA cycle. First, we control or define an algorithm and actuate, and after the actuating, understand what happened, sense the outcome, and then from there, find out what correction needs to be done and correct the actuation so that the control can be done. That's the fundamental principle of control, which I explained on Monday. I don't want to get into the depth today. If you want, you can watch the video from Monday. I've spoken about that in detail. And smart manufacturing is basically using hardware and software technology for assisting initially to fully managing repetitive tasks within an environment or ambience. That is a fundamental definition that I would go with. And with that very brief definition, let me directly talk about the various cycles which are important to the one second, pointer options. Yeah, so I wanted to just get the pointer on so that I can see the I can show you something in case it is required, so you can see the pointer on the screen. So with that, let me talk about the various regulating cycles. I had said that these cycles are quite standard in any company, any manufacturing company: the product cycle, process cycle, people cycle, performance cycle, productivity, programming, and finally progression cycle. These are the 7 cycles that I've identified, and today we will be talking about the product cycle. I spoke about the first aspect of the product cycle, the control phase or the plan phase, where what can be done in terms of smartness in that particular phase. Then on Wednesday, I spoke about the minimum viable product, which is what that would be done once the product idea is there, to really put it into practice and give it to somebody to test it out. And then spoke about how do you ensure or how do you check out whether the product, whatever we have made, is has the potential for running a business, and whether it is profitable. And for that, in that particular phase, what kind of smart activities can be done. And then yesterday I spoke about the uh, what would happen if, suppose, let us say, once you have checked that, and how would you go to the next level. That is what I spoke about yesterday, to see if the activities that we did are stable and capable, and based on that decide to go to the next level or continue to stay in the same level. And today I would be talking about the last activity of this cycle, the last phase of the cycle, which is the act cycle, or you can also call it as the the correction cycle, the correction phase of the control cycle. The correction phase is where you understood something, now you correct it so that the control becomes even more targeted and even more goal oriented. So in this phase of the product cycle, what can be done in terms of smartness? The first thing is what is called as quality function deployment. I'm not sure whether you heard of that. It's a very old tool, very old methodology which existed for a long time. And the only thing there is that it needs a lot of effort, because it's not going to be simple to use the quality function deployment methodology. Normally, you need to have conduct a workshop with experts from all areas where you are trying to transfer the product, the customer wishes or the customer needs and expectations to product specifications, and product specifications to drawing, drawing to process, process to process parameters. So that's a macro explanation of quality function deployment. This is one of the tools that I've been using quite regularly, because that's something which is very structured way of finding out what specifications and what components are required in a product or a solution to meet the customer needs, and how much each of these contribute to the various customer needs. That's also equally important to understand, and that's the essence of trying to create what is called as a function cost analysis matrix, which I explained the other day in the potential and profitability phase, where you really do that, use that particular methodology that basically is derived from the quality function deployment. Then the next one which can be done, which is phenomenal, is to do 3D tolerance stack analysis, or tolerance analysis you can call it as, wherein the component, let us say this is the component that we're talking about, there are multiple parts, individual components in this particular pen, and imagine that you could put this all on the three-dimensional drawing or a model, and then try to understand how are the tolerances of each of these stacking up, so that you understand what would be the variation you get in the final assembly. And that is something which is very essential, because that using this 3D tolerance analysis, the tolerances can be optimized so that we don't really run into a situation where the tolerance cannot be maintained, or the tolerance is too loose, in the sense though the process is extremely capable, the tolerance is very loose, so that the process can drift then in the entire tolerance. So the average which you get in terms of the production, in terms of the components which you source, that could be drifting from one end to the other end. So there again, it's very important to make sure that the tolerance is very what should I say, optimal when it comes to the process. So if the process is extremely capable, even though it is not required, my recommendation is to go in for a tight tolerance, because then your X bar, or the average of whatever components you are getting, will be for a particular target value. I think many of you would have heard of what is called as a Taguchi function, where the principle is to really aim at a target value, and this target value can be achieved using the 3D tolerance analysis, and it's really phenomenal. And for that, you need computers, you need smartness. It's not possible to be done without any simulation, because imagine physically trying to talk about a tolerance of 20 microns or 100 microns, and then try, first of all, the dimension itself is too small. So you need to have a massive scale, and if that happens, then the overall size of the component becomes humongous. You can't really manage physically. So therefore, a computer is required for that. That is one which can be done. The other place where the smartness can be introduced in this product development phase, or I call this the product development as the last phase of the product cycle, because that is where the product gets corrected and the product gets further developed. So it's a continual improvement, continual cycle. It's a cycle which goes round. You do the product development and work on the product idea, do the minimum viable product, check the potential and profitability, and get back to the product development. That cycle keeps on going on for some time before we really decide to go to the next level, because this has to be to some extent matured. It's essential that this initial phase is done. In many companies, they call it as the advanced development of products. Some companies call it as functional development products. Whatever be the name of the department or the function which does this job, it's extremely important that the product maturity is achieved to some level before the process is thought over, because otherwise we'll only be running helter-skelter. So that's something which is very essential. So for doing that, 3D tolerance analysis is very useful. Then the calculation automation, this is something which is phenomenal. It could be either using some theoretical numbers or theoretical formulae, or it could be empirical also, wherein we are trying to optimize it. I remember in one of the roles which I did, we did that calculation automation for finding out what is the optimum dimension that you need to maintain on a particular component, because that involves a lot of iterations. You need to really find out a particular dimension, and after that do the finite element analysis, and then get back and then see if the dimension changes, what would be the stress levels and what happens where, and again get back. So that iteration which you do can be automated. That is what I call as a calculation automation for finding out and designing the components. That's again another area where smart manufacturing concepts can be used. The other two areas where it can be used is for highly accelerated stress screening. This again, first once the simulation, once the physical activity is done, then after that that entire thing can be simulated in a computer. Then based on the components that we have got, you can run the simulation program and find out where the wear out would happen, and that again needs a lot of scientific basis. And here both, mind you, both empiry and theory is in place. It's not just theoretical, because many a times you can't really understand what the cause and effect is, but you'd have seen in true life, in reality, as to what's going to happen if it is X and what's going to happen if it is Y. So based on that, some model can be built up, and then this has can be done. Then again, another interesting where smartness can be used is highly accelerated life testing. Imagine a particular bearing has to be working for a million hours, for example, or a million days, or a million hours. Now, if that is the case, then one possibility is to run that bearing for 1 million hours to find out if it really going to fail or not. Or we could increase the load on the bearing significantly and exponentially. And for that, to find out what needs to be increased, factorial experiments have to be done. And once that is done, you run the bearing for a shorter time, but with extreme load, or it could be with extreme corrosive oils in the bearing, so that the bearing gets worn out much faster. And then we try to analyze what got worn out and how is it going to affect the function of the particular product. And that's again another thing where some amount of smartness can be used. Where I'm talking about, when I say smartness, I come back to the earlier slide, which is important, the first slide which I said. Smartness is very simple. You have a control. Control means you think as to what could be done. You can also call it a hypothesis. You can call it a hypothesis, a control, which talks about some kind of an algorithm, and from that algorithm actuate it. Actuate means do the actual activity, then sense what happened, and from there do the correction, and again do the algorithm. So this cycle of controlling, actuating, sensing, and correcting is something which is very, very essential, and that's what is the key to really developing and ensuring that the HALT test is very effective, and also it really works very, very robust in terms of making sure that you really understand what are the vulnerabilities in the product which can be addressed. So with that, I spoke about this yesterday. Actually, the sequence has changed. I should have done it today. It got changed. I'm sorry. Next time, next week, I do it the right way. So next week, I'm going to be talking about, imagine that we have done this cycle quite a number of times, maybe some 3 or 4 iterations we have done in this cycle. We just go around product development, product idea, viable product, and profit, the potential and profitability, and again do the development. This entire cycle has gone through, let us say, 5 to 6 times. We have got some kind of a base product available now. But of course, that can further get developed. The development happens in parallel. At that point, when that is done, then we have a choice of checking whether there is some amount of stability. I said stability is important. If the stability is there, then we need to check whether the capability is there. If both are met, then we go to the next level. Otherwise, we continue in the same level, running through the product cycle itself, going round and round in circles till the time that it becomes stable. Once it becomes stable and capable, then we can progress to the next level, which is the process cycle. And that's what I'll be talking about next week. Process cycle is all about starting with the value stream, understanding how the entire product would be made, and after that, we go on to other topics of the process cycle. So with that, thanks a lot for watching. For those of you in India, have a nice evening. For those of you outside India, have a great day, and see you both on Monday at 8:30 Indian Standard Time, more or less this time. Thank you so much, and goodbye. Have a nice weekend.